Okay, let us just take a short video to recapitulate, to remember why we use the method of averaging, and the next topic will be the method of multiple scales. So let us go back to a differential equation that we are familiar with from higher order averaging, which is this. Okay, so that will be 0. I'm not saying it is 0, but that will be 0. Epsilon is small, it's in Lagrange standard form. Okay, now you may say that we will try to solve this using a regular perturbation expansion, and it will not work. So let's try that. Let us say n equals 2 for the moment. Let us say x solution is equal to add and then epsilon to the power k times x k of t, k equals 0 to n. So this is the solution. So over here I am not doing anything with the time, and this is some function of time independent of epsilon, this is another function of time independent of epsilon, and so on. Okay, so then I have dEA is equal to substitute x of t equals x solution in dE, but I'll have to do expand. Sorry, go here, expand, then I'll have to do Taylor, I can even do convert polynomial. Okay, so that's my system, and you see what happens is this is the order 1 term, so x0 dot is equal to 0. That means x0 is equal to a, some constant, some initial condition. Okay, so I come here and I say dEA, well, let me do the first, let me do S1 is equal to x0 of t equals a, some constant, and let me say x solution is equal to substitute S1 in x solution. So I've substituted that already. So far it looks good, although it will soon break down, and I say dEA is equal to expand substitute S1 in dEA. Okay, very good. I can what I need to do is collect for epsilon, or collect in terms of powers of epsilon to get a cleaner expression. Okay, and here we are, and we can solve this now. So what we will do is we will say temp is equal to the coefficient in dEA of epsilon to the power 1. There we have it. We need an initial condition for x1, could be 0, or we'll temporarily put some number b and then we will see what happens. So we will say t solve temp with the initial condition x1 of 0 equals b for x1 of t. Okay, so that's the solution, and it does not seem very bad. Okay, so there is a cosine part and something, so that's not a problem so far. So then I say temp 1 is equal to that, and then I say x solution is equal to substitute temp 1 in x solution. So that's my solution so far, and I will say dEA is equal to expand substitute temp 1 in dEA. I should do collect epsilon, and you see order 1 terms are gone, order epsilon terms are gone, and now I have order epsilon square only. So then I say temp is equal to the coefficient in DEA of epsilon to the power 2, and then I say dsolve temp, and then I say x2 of t 0 is equal to some number c, and I solve this for x2 of t. And I expect trouble here, so let me look for it. I'll find it. Here is trouble. So you see this one, this a square t is going to grow and grow and grow. This is an order epsilon square quantity. So by the time t is equal to order 1 by epsilon square, this solution will break down. This will be fine, this will be fine, this will be fine, fine here, fine here, fine here, 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 constant, constant, no problem. But this will kill you. So if a is not 0, then your solution will break down. If a is 0, then you will survive at this order, but then at the next order you'll have some trouble. So let's see that. So we will come back here, we'll start again, and then here we will say 3. We will come here, and then as we have decided to try 0, I'll put 0 here. Then I come here, and then I pick out this one, you see, and then I call this one a. Now this a is not 0. Oh, well, let me leave it as b, doesn't matter, no confusion. So now it's just a constant b. I substitute that in, and I collect, and epsilon square is there, so that's not a problem. So I collect that, and I solve it with an initial condition of c, and then I call this temp1, and then I say xsol is equal to substitute temp1 in xsol. Okay, so here is my epsilon b, and here is the sinusoidal part. This one remains to be found, and then I come here and I say DEA is equal to expand substitute temp1 in DEA, collect for epsilon. Okay, order epsilon cube. Now we have to solve this, and what we will do is we will say temp is equal to the coefficient of DEA epsilon 3 excuse me, and then I will say dsolve temp x3 of t, 0 equals, now I don't want to say d, I'll say e, some number, and I say solve for x3 of t, and this seems all right, but then I think that means it will work out badly at the next order. So let's go here, okay, so I'll call this temp1, and I'll say xsol is equal to substitute temp1 in xsol, and so I have, this is all right, this one's bounded, this one is bounded, and I still have to find this one, and then I will say DEA is equal to collect, expand, substitute temp1 in DEA, and now I have only epsilon to the 4th, so that's all right. And then I say temp equals the coefficient in DEA of epsilon to the 4, and then I say dsolve temp x40 equals some number f, x4 of t. B square t. So if you don't make b equals 0, this will break down. And in this way, as you proceed, you will see that basically you will just have the 0 solution. If you have any non-zero solution, the system will break down. This is why regular perturbations fail, right? Let me regular perturbation expansions break down over the time scale of interest. You are interested in x of order 1. So if you have to start from a very small initial condition, then you wait for it to get big, but the moment it gets big, it breaks down. Okay, so x4 has to remain small. If b is not small, then by the time t is order 1 by epsilon square, x4 is no longer small. So it is becoming big. That means it is becoming comparable to x3, right? So and then your expansion breaks down. So that is why we use averaging and multiple scales. The next lecture will be about multiple scales.